Gravimetric stoichiometry, these are big words, but it's a pretty simple process, but it's a very important process. So basically, it's how we calculate mass. Gravimetric means mass of reactants or products, and we do this using stoichiometry, the relationships found in the balanced chemical equation. It's a very important process for chemistry people or chemical engineers. You need to know how much raw material you need to make a specific amount of product, and you'll need to know how much doesn't get used up. So you'll use this math many, many times in this course and in any future chemistry classes. It starts the same way basically as using chemical formulas, in that the first two steps are the same. You have to have a balanced chemical equation, and then you put in the amounts that you know underneath, including ratios. And then what you have to do is identify the units that we want for our answer, and then we find the ratio that contains it. And this is where we start from. Then the second ratio or value that you pick depends on what you need to cancel from the first ratio, which is actually whatever was in the denominator. So on until all the units cancel except for the desired ones. Okay, so I'm going to do an example with you. Okay, so carbon dioxide is produced by astronauts and can be removed with lithium hydroxide. The reaction produces lithium carbonate and water. An astronaut produces an average of 1 kilograms of carbon dioxide per day. What mass of lithium hydroxide should engineers put on board a spacecraft per astronaut per day? This is pretty important to figure this out before they leave, because there's no 7-Eleven or Walmart or Sobeys where you can just pop out and get what you don't have. So when you send up a payload on a spacecraft, you have to make sure your calculations are correct. So first thing to do is balance the chemical equation. So we need a 2 here. And we're going to put in what we know. We know that we have 1 kilogram, or 1 times 10 to the 3 grams of carbon dioxide, and I put it underneath carbon dioxide. I know that the molar mass, because I can calculate it, is 44.01 grams per mole. Actually, I'm going to write that as a ratio. You always can find molar mass. So even if they don't give you this ratio, you've got to remember that it's yours. It's in your back pocket. This is something that you can find out if you know the name or the formula. We want to find the mass of lithium hydroxide, so we want grams of LiOH. And we know the molar mass, because we can calculate, is 23.95 grams per 1 mole. And this is LiOH. Put your units in. Units are very important. So we want to find the mass of lithium hydroxide, so grams of LiOH. So this is where we need to look. We have 3 different sets of values here, and we're going to use them to help us find what we need. So we want grams of LiOH. So is there anything here with grams of LiOH? Yes, there is. We have it right here in our molar mass. And grams of lithium hydroxide are on top. So we're going to leave this ratio like this. We're not going to turn it upside down. So 23 23.95 grams of lithium hydroxide is in every 1 mole of lithium hydroxide. So what we need to do is we need to now look at the denominator, and we need to get rid of moles of LiOH. So we've used this ratio already, so we can't use it again. So what we're missing is we're missing our mole ratio. And our mole ratio is, there's 1 carbon dioxide for every 2 lithium hydroxides. And I got those from the balanced chemical equation, the coefficients in the balanced chemical equation. Now, we can write it as 1 CO2 to 2 LiOH, or we can write it as 1 and 2 moles. So 1 mole of CO2 and 2 moles of lithium hydroxide. Now initially it might seem that there's a lot of work in doing dimensional analysis, but once you get the hang of it, you fly through these questions. Now, this is our mole ratio, but we want moles of lithium hydroxide out of this part here, so below. So we have to flip this so that LiOH is on the top. So when we put in our mole ratio, we will have 2 moles of LiOH for every 1 mole of CO2. So now our moles of lithium hydroxide cancel, because one's on top, one's on the bottom, but just the units, not the numbers. The 2 and the 1 stay. So now I've used the mole ratio. I can't use it again. Now I need to get rid of moles of CO2. So what of the other 2 numbers has moles of it? Well, see right there, we've got moles of CO2 in our molar mass. So the next ratio, we need to have moles of CO2 on the top so that they cancel with this moles of CO2. So 1 mole of CO2 for 44.01 grams of CO2. So we cancel the units, moles of CO2, but not the numbers. And we've used that ratio. Now we get rid of grams of CO2. We only have 1 number left, and that happens to be the 1,000 grams of CO2. So the grams, the G, CO2 cancel, but we don't cancel the numbers. So then what you do in your calculator, because we've got multiplication signs followed in between the ratios, what you do is you multiply every number on the top and you divide by every number on the bottom. So if I was putting this in a calculator, it would be 23 point, you don't have to show this, 23.95 times 2 times 1 times 1 times 10 to the 3, or 1,000, divided by the ones, divided by 44.01. So I didn't show the divide by 1 for the first ones, because any number divided by 1 is the same number. So we multiply every number on the top in your calculator and then hit divide by any number on the bottom, and you've got your answer. It seems a lot of work, but it's actually going to go faster once you get the hang of it. So The answer is 1088.4 grams. We can only have 3 significant digits in our final answer because there's 3 significant digits in our initial mass. So 1090 grams of lithium hydroxide. Now, the benefit to doing dimensional analysis, other than it is quicker once you get the hang of it, is there's no intermediate calculations. So you don't lose marks for rounding early or dropping sig figs or for not putting in your units, because there's only one calculation and your units are following through on each step. So you have to put in your units. So you could lose half a mark for each individual step in a regular calculation, and you won't lose it the same way in this one. So all you would need now is a statement. So you would just write out 1090 grams of lithium hydroxide are used per astronaut per day. Okay. Sometimes your final answer, they're not looking for grams, they're looking for number of molecules or number of atoms, but it's the same first couple of steps, and then we need to use Avogadro's number. Okay, so we have a balanced chemical equation. We know that we're looking for molecules of chlorine. That should say chlorine, not chloride. React to produce 50 grams of disulfur dichloride. So the molar mass of disulfur dichloride is 135.02 grams for every 1 mole. That's S. Okay, so we want the number of molecules. So we know that we have to use Avogadro's number. And we will need a mole ratio of S2Cl2 and chlorine. So there's 1 mole of Cl2 for every 1 mole disulfur dichloride. So pretty much this is where we're starting. Hopefully it's enough information. So we want molecules of chlorine in our answer. So what ratio or value here contains molecule of Cl2? So it's this first one. And molecules of Cl2 have to be on the top, so we're going to use Avogadro's number as it is. One mole of chlorine. All right, so we've got to get rid of moles of chlorine. Can't use Avogadro's number again. So we need something with moles of Cl2. There's only one thing, and that's our mole ratio. So we need to have moles of Cl2 on top so that they cancel the moles of Cl2 in our first ratio. So our mole ratio, we can use 1 mole of Cl2 for 1 mole disulfur dichloride. So moles of chlorine, not the number ones, just the units, cancel. Now we need to get rid of moles of disulfur dichloride. We have 2 values left, and one of them has moles of S2Cl2 in it, and that is the molar mass. However, we need moles on top, so we have to invert this, flip it over. So 1 mole S2Cl2 on top, 135.02 grams on the bottom. So now the units, moles of S2Cl2, cancel. The ones stay. Now we've got grams of S2Cl2 to get rid of, and we happen to have grams of S2Cl2. In fact, we've got 50 of them. So now we've used up everything we have. Our grams of S2Cl2 cancel, so those units are gone. So the only units we have left right now are these molecules of Cl2. And that's exactly what we want in our answer. So it's not random what we put next. What comes next, what ratio comes next, always depends on what units are in the bottom of the ratio that we're using. So in this calculation, in your calculator, you would put Avogadro's number, 6.02 times 10 to the 23rd, times 50, divided by 135.02, because the ones aren't going to change anything. And your answer will be 2.23 times 10 to the 23 molecules of chlorine. So to make 50 grams of disulfur dichloride, 2.23 times 10 to the 23 molecules of chlorine are used. Now, we don't often ask for molecules because it's not something that's easily measured. What's easily measured is grams. So 95% of the time, they will be asking what mass of chlorine is needed to react to produce 50 grams of disulfur dichloride. So this is dimensional analysis. The more you do it, the quicker you will get, the shorter the time it will take you, and the less paper you're going to end up using to do your math.